All right, part two of special relativity. So we ended last time with the fact that the speed of light is constant, independent of the observer and the observer's frame. So let's look at some of the implications of that. So imagine this train car is going along and these two lights flash. So boom, they flash. And let's look at the world from what observer B sees. Observer B sees, got to remember, the light emits from these 2 points and the train moves on after that. So observer B sees the light come from there and from there, and it reaches him at the same time, right? But let's look at what's happening inside the train as far as observer B is concerned, right? If you look at where the woman is when the light arrives, the light goes from here to there and from here to there, all right, to line up with where she is when the light actually reaches there. So what really happens is the light hits the woman, as far as observer B is concerned, the light hits the woman from the right before it hits the woman from the left. All right? So simultaneity is no longer absolute once you say the speed of light is independent of your reference frame. All right? It's independent of your reference frame. Let's look at another example of what this means. And what we're looking at is going to be called time dilation. So imagine you're an astronomer on the, astronaut on the space shuttle, and you set up this little experiment. You're going to shine a light, you're going to bounce a light off a mirror, boom, boom, and you're going to measure how long it takes for that to happen, right? So just boom, boom. It's the time it takes to make half the trip, or from here to the mirror, is d divided by c, right? So the total round trip time, delta t, is twice that, or 2 over c times d. Very simple. This is a problem you guys solved on the last test, right? It's the exact same problem as communicating with Voyager 1. So delta t, 2 over cd. Okay. Now imagine you're watching this happen, and you're not on the space shuttle, you're on the Earth, right? So you watch the light go along this path. And the length of that path is defined by the velocity of the shuttle, right? And d, this side. So length of that path, the shuttle goes a total distance of 2L, right? So L is just the velocity of the shuttle times the amount of time it takes for the light to go up and down, right? L is v delta t over 2. Since L is only half the distance, the 2 is there. Okay? So that's L. And so if we look at what's going on, here you are, you see it go S and back down, right? And S is just d squared plus L squared, right? Just the Pythagorean theorem. So you see it go a total distance of 2s. So the amount of time you see the light take is delta t is 2s over c, which is 2 over c d squared, square roots of d squared plus L squared. That's not the same as what we got for what the astronaut sees, right? The astronaut, 2 over c d, you, delta t is 2 over c square roots of d squared plus L squared. So you see something different. All right. So what does this mean? Well, let's start with delta t is 2 over c. Sorry. Okay. So this is certainly delta t is greater than delta t 0. So for you, the observer outside of the moving inertial frame of the space shuttle, it takes longer than it does for the astronaut. Right? You see this process take longer than the astronaut does. So time is different for the astronaut and for you. If we substitute back in for L and work through the math, right, what we end up with is delta t is 2 over c squared, it's d squared plus v delta t over 2 was L, right? V delta t over 2 squared. Let's square everything. So delta t squared, 4 over c squared, d squared plus v delta t over 2 squared. And I rearrange a little bit here to make this 2 over c d squared. That's our old delta t0, right? Right here, that's delta t0 that the astronaut experienced, right? And this is v squared over c. So the result, when you take that into account, is delta t and collect like terms, right? The delta t squared minus v over c squared delta t squared. Okay, pardon me. And in the end, we get delta t is the time that we see standing on the Earth at this experiment to take is the time the astronaut experiences divided by this 1 minus v over c squared. Well, we call this whole thing 1 over 1 minus v over c squared gamma, and we just write this delta t equals gamma delta t0. So time in your reference frame, all right, differs by time in an inertial frame moving at a velocity v relative to you by this factor gamma. So what does gamma look like? Now, if you'll notice, I plotted out gamma here for you, and I've done it with a log scale over here, so you can actually see some of the change in gamma. So here we are. Here are the velocities down here. This is the speed of light, right? 3 times 10 to the 8th. So at 0.5, we've not moved much. At 1, moved just a little bit. At 2, right, we're up probably around a value of 2 or 3. At 2.5, we're getting up to a value of around 4, but then it makes this turn as you get close to the speed of light, right? And it shoots up dramatically. So this is a limiting factor and tells us the time dilation in our normal world, right? Our normal world being way down here. Time dilation in the normal world is essentially, there's essentially none, right? That if I watch you going down the road in your car, you're experiencing time flow at almost exactly the same rate I am. Kind of cool that it doesn't hold once the velocities become relativistic. Once they become relativistic, the frame in motion experiences a slower flow of time. All right, that's it for part 2.